Welcome back, everyone. Today, we're going to be taking a deep dive into something that I think is really fascinating and maybe even a little bit spooky:
Yeah,
quantum entanglement.
definitely a bit spook. Even Einstein thought so.
Yeah, he called it spooky action at a distance, right?
That's right. And you know, it's funny because for a long time, it was really just this theoretical idea.
Right thought experiment.
Yeah, but now it's actually becoming like a really practical foundation for a lot of the advancements we're seeing in things like quantum computers and communication.
Yeah, it's not just theory anymore. It's like real world stuff,
Yeah.
which I think is so cool.
Absolutely.
So, um, I guess to get started, our main source material today is this paper titled Quantum Entanglement: Principles and Research, Progress in Quantum Information Processing, which I think is a pretty fitting title.
Yeah, definitely sums it up.
So maybe for our listeners who have maybe heard of quantum entanglement but don't really know the details,
Mhm.
how would you explain it in simple terms?
Okay, so imagine you have two coins
Okay.
and you flip them at the same time. Now, if you see one land on heads,
You know the other one's tails.
exactly. You know instantly, right? Even if they're miles apart.
Right. Well, I mean, with coins, they'd have to be pretty close.
Right, of course.
Well,
But with entanglement, it's like those coins could be light years apart and they'd still have that instantaneous connection.
whoa. So it's like they're communicating faster than the speed of light.
That's the thing that really baffled Einstein. Like, how can this be happening without breaking the rules of physics?
Right, because nothing can travel faster than the speed of light.
Exactly. So it's like, how is this information being shared between these particles instantly across vast distances?
It is spooky.
Very.
So, okay, let's say we have these entangled particles. How do scientists actually measure how entangled they are? Like, is there a unit of entanglement or something?
It's not quite that simple. Unfortunately, there's no like entanglement meter. You can just point at something.
Right, huh?
But there are mathematical ways to represent it, like entanglement entropy, for example.
Okay, but I'm guessing that gets pretty complicated.
Yeah, it can get into some pretty heavy math.
Maybe we can just stick with like a scale then, right? Like zero entanglement, meaning the particles are totally independent, and then maximum entanglement where they're completely linked.
Yeah, that's a good way to think about it for our purposes.
Okay, so that makes sense. But how do scientists even create this entanglement in the first place? Like, what's the process?
It's a bit like a delicate dance. They use something called LOCC, which stands for Local Operations and Classical Communication.
LOCC.
Yeah, it's basically a set of rules for how you can manipulate these entangled particles without breaking that connection between them.
So it's like a special toolkit for handling something really fragile.
Exactly. And what's even crazier is that entanglement isn't limited to just tiny particles like electrons or photons.
Wait, really?
Yeah, scientists have managed to entangle atoms, and there's even theoretical talk of entangling larger
Oh,
objects.
hold on. Like, what if we could entangle two apples?
Theoretically, it might be possible, but the challenge is maintaining that entanglement, especially over long distances and with larger systems.
Yeah. I guess that makes sense. Like, the bigger the system, the harder it is to keep everything perfectly synchronized.
Exactly. It's like trying to keep a million soap bubbles from popping all at the same time.
Yeah, that's a great analogy. So, okay, we've got this seemingly impossible connection, this spooky action at a distance that even Einstein couldn't fully wrap his head around. But what can we actually do with it? That's what I'm really curious about. Like, what are the practical applications of this entanglement stuff?
So that's the big question, right? What can we actually do with this weird entanglement stuff?
Yeah, that's what I want to know. Like, does it have any real-world uses?
Oh, definitely. In fact, it's already starting to revolutionize certain fields like quantum computing.
Quantum computing? Oh, yeah, that's another one of those things that always sounds super futuristic to me.
It kind of is, but it's also becoming more and more real every day.
Yeah.
And entanglement is a big part of what makes it so powerful.
Okay, I have to admit, I'm still a little fuzzy on how quantum computing actually works. Could you give me like a quick crash course?
Sure. So, you know how a regular computer uses bits, right?
Yeah, like zeros and ones.
Exactly. They can be either 0 or 1, like a light switch on or off.
Hmm.
But a quantum computer uses qubits, which are more like a dimmer switch.
Okay, so a qubit can be 0, 1, or somewhere in between.
Exactly. It can be in what we call a superposition, which means it's both 0 and 1 at the same time.
Ooh, that's kind of trippy.
Yeah, it's one of the key things that makes quantum computing so different from classical computing. But here's where entanglement comes in. It allows those qubits to be linked together in a way that lets them influence each other, even if they're physically separated.
So like if you change one qubit, it instantly affects the others, even if they're miles apart.
Exactly. It's like they have this secret communication channel that transcends space and time.
That's mind-blowing. So basically each qubit has a direct line to every other qubit, allowing them to work together in a way that regular bits can't.
You got it. And that gives quantum computers this massive advantage when it comes to solving certain types of problems. It's like having a team of experts working together instead of just one person trying to do everything.
Wow. I can see why people are so excited about quantum computing then. But if it's so powerful, why isn't everyone using it already?
Well, there are still some major hurdles. One of the biggest is that building and controlling a quantum computer is incredibly challenging.
I can imagine it's probably not easy to keep all those qubits in their superpositions and entangled states, right?
Exactly. Those states are incredibly fragile, like super sensitive to any kind of noise or interference from the environment.
So it's like trying to build a computer out of soap bubbles, one wrong move and the whole thing pops.
Yeah, it's a really delicate dance. And on top of that, we need to figure out how to scale these systems up to handle the massive number of qubits needed for practical applications.
So it's still early days, but it sounds like the potential is huge.
Definitely. Now, another area where entanglement is already having a big impact is in communication, specifically in something called quantum key distribution, or QKD.
Oh yeah, QKB, we
Wow.
touched on that earlier, but I'd love to hear more about how it works and how entanglement plays a role.
Sure. So imagine you have two people,
Hmm,
let's call them Alice and Bob,
okay.
and they want to send a secret message to each other securely. They each receive one part of an entangled pair of particles.
Okay.
Now, because those particles are linked, measuring the state of Alice's particle instantly affects Bob's particle no matter how far apart they are.
Right, because of that spooky action at a distance.
Exactly. And here's the key. By making specific measurements on their particles, Alice and Bob can generate a random string of bits that only they know.
Okay, and that string becomes their secret key.
You got it. And the beauty is that any attempt to eavesdrop on those particles would disrupt their entangled state.
So it's like an unbreakable code because
Yeah.
any attempt to crack it would immediately be detected.
Exactly. That's what makes QKD so powerful. It's not just about complex algorithms that could potentially be broken, it's about exploiting the fundamental laws of physics to guarantee security.
Wow, that's incredible. So it's like having a secret language that only you and the person you're communicating with can understand, and anyone else trying to listen in would just hear gibberish.
It's a pretty good analogy. But of course, transmitting these delicate, entangled particles over long distances presents its own challenges.
Yeah, I was just thinking that it can't be as simple as sending an email, right?
Right. It's not easy. You have to be really careful not to disrupt that fragile, entangled state.
So how do they do it?
Well, fiber optic cables offer some promise for shorter distances, but for truly long distance quantum communication, we might need something even more advanced.
Like what?
Satellites.
Satellites. Whoa, hold on. Are you telling me we could have a quantum internet beamed down from space?
It's not science fiction, it's actually being researched right now. In fact, our source material mentions some exciting work being done with satellites like China's Mudshis, which has successfully demonstrated entanglement-based communication between space and the ground.
Wow, so a space-based quantum internet could actually be a reality someday.
It's definitely a possibility, and it could have huge implications for global communication.
I can imagine. But it also makes me wonder about the bigger picture. Like, as this technology becomes more widespread, what kind of impact could it have on our world? What are some of the potential implications we need to be thinking about? You know, it's funny, we've been talking about all the practical applications of entanglement, but what really gets me is like the bigger picture.
Oh, yeah.
What does it all mean? You know, what does it tell us about the nature of reality itself?
That's the million-dollar question, isn't it?
It really is. I
Hmm.
mean, it's one thing to say, okay, these particles are connected across vast distances, but like, what does that actually mean?
Right. It's not like anything we experience in our everyday lives.
It's like they're playing by a completely different set of rules.
Exactly. And it really challenges our assumptions about how the universe works. We're used to cause and effect happening in this local step-by-step way.
Right.
But entanglement suggests that things can be interconnected in ways that we can't even really comprehend.
So like rather than separate independent objects, it's more like everything is part of this giant entangled web.
That's one way to think about it. Yeah, some physicists believe that entanglement points to this holistic view of the universe, where everything is ultimately connected.
Wow, that's kind of trippy.
It is, and there are other interpretations too. Some people think that entanglement might be evidence of a deeper level of reality, like a hidden realm beyond our current scientific framework.
Okay, now that's getting really out there.
Yeah, but that's what's so exciting about it. Entanglement forces us to question our assumptions about the very nature of reality.
It's like we're just scratching the surface of something truly profound.
Exactly. And as we learn more about entanglement, who knows what other mysteries we might uncover.
Right, it's like this whole new frontier of scientific exploration.
It is. And as we wrap up this deep dive, I want to leave you with one final thought to ponder if we can link particles across vast distances instantaneously influencing each other, what other seemingly impossible things might be possible? What other mysteries might the universe hold waiting to be unlocked?
Yeah, that's a great question. And, who knows? Maybe one of our listeners will be the one to unlock those secrets someday.
I wouldn't be surprised.
Well, that's all the time we have for today. Thanks for joining us on this journey into the fascinating world of quantum entanglement.
Thanks for having me.
It's been a pleasure. Until next time, keep exploring, keep questioning, and keep your mind open to the wonders of the universe.